This presentation is based strictly on the bibliography and it does not contain our own original results. Binary and n-ary topological spaces. Binary topological spaces have been introduced by Hindu mathematicians Jyoti and Tangavelu in 2011. Later, this idea has been reproduced in generalized Chasser's framework by Tivagar, by Mustafa, and by Ahengar, Maitra, and Chaturvedi, 3 independent approaches. They are also in our bibliography. Moreover, Saralakshmi and Kamaraj founded n-ary spaces, which are n-dimensional extension of binary topologies. Very natural, but in some sense interesting. According to Jyoti and Tangavelu, binary topology can be defined in the following way. Assume that we have two non-empty universes, X and Y. A binary topology from X to Y is a family contained in Cartesian product of power sets. Not in the power set of Cartesian product, but in Cartesian product of power sets that satisfies these axioms. Clearly, as you can see here, these axioms are very natural and these are typical topological axioms, but in our new binary environment. For example, this pair, empty set. Empty set belongs to our binary topology. Universe belongs to, and moreover, we have closure under finite intersections and closure under arbitrary unions. For example, consider these two finite sets, x equal to abcd and y equal to 1, 2, 3, 4, 5. Among many binary topologies which can be established, we may define M1 and M2, for example. You can discuss them or meditate upon them for a while. It's worth to note that the concept of binary topology from X to Y is independent from the idea of product topology on the Cartesian product of X and Y. Recall that if we have two topological spaces, X with tau X and Y with tau Y, then the product topology in or on their Cartesian product can be generated by the following basis. Products of non-empty open sets. One set from X topology and one set from Y topology. However, in general, Cartesian product of power sets is something different than power set of Cartesian product. However, maybe we can identify A product B with an ordered pair AB. In some sense it's possible, but observe that empty set does not belong to the product topology. We may treat product topology as binary if we identify empty set with an ordered pair empty. However, on the other hand, and this is much more interesting, consider, for example, X equal to ABC and Y which consists of 1, 2, 3, 4. And now we have the following binary topology, among many others. The only non-trivial set, non-trivial element is this one, which consists of singleton of A on the left side and empty set on the right side. However, it wouldn't be sensible, it would be rather arbitrary and very, maybe even ridiculous to identify this pair with singleton of A or with empty set. So indeed, these are two different concepts, albeit in some sense, or sometimes there are certain connections between them. Now we have n-ary topology. According to Saralakshmi and Kamaraj, if we have n non-empty universes and certain family contained in Cartesian product of power sets of these universes, then T is n-ary topology if and only if the following axioms are satisfied. N-ary empty set belongs to this family. N-ary, well, so-called absolute set belongs to this topology, and of course there is closure under finite intersections, and arbitrary unions. Clearly, these are typical topological actions, or rather than their n-ary counterparts. We may and we shall consider several examples of n-ary topologies. But first, let us say that in our notation, n-ary point x1 to xn belongs to an n-ary set if and only if it belongs to the product of components. And of course, the notions of n-ary union, intersection, complement, and difference are defined component-wise, just as it was in the case of binary topology. Moreover, we say that two n-ary sets are n-ary disjoint if the sets in the corresponding positions are disjoint. Here we have several examples of n-ary topologies. In this case, n-ary null, void, or empty set, and also a collection of each n-ary sets such that certain distinguished point is contained if belongs to each of them. This idea here is similar, but here we have certain distinguished n-ary set b1 to bn, which is contained in a1 to an. Now we have diagonal of x with the assumption that we have n copies of a1 and a1 is contained in certain universe x. And also this n-ary topology b1 bn contained in a1 an, and we take empty set, absolute set, and both b1 bn and its superset a1 an. More interesting examples like n-ary Euclidean topology over real line are to be found in bibliography, and some of them will appear in our further presentations. There are also some subtle issues which make n-ary spaces with topology or without interesting. For example, assume that we have finite non-empty sets satisfying one of the following conditions. When n is greater than 2, so we have at least x1, x2, x3, then we assume that cardinality of each set is greater than 1. If n is equal to 2, then we have cardinality of x1 greater than 2 and strictly greater and cardinality of x2 greater or equal to 2, or vice versa, analogous condition here. So satisfying one of the following conditions, and now cardinality of power set of Cartesian products is strictly greater than cardinality of Cartesian product of power sets on the right side. Setalakshmi and Kamaraj proved also some other important combinatorial properties of n-ary spaces, so look to the bibliography. There's also an interesting notion of somewhat empty set. Somewhat empty set. We say that n-ary set is somewhat empty if we have certain, at least one non-empty component and at least one empty component in this ordered n-tuple. Now the following theorem is true. First, let S denote the collection of all somewhat empty n-ary sets in Cartesian product of power sets of x1, x2, and xn. Let M be this product, Cartesian n-ary product of power sets, but without S. That is the collection of all n-ary sets on our absolute universe other than somewhat empty sets. Other than somewhat empty. Then, and this is our theorem, M can be considered as a proper subset of product of Cartesian, of a power set of Cartesian product of universes. Strictly speaking, let phi be function from M, we defined M here, to this power set of product of n universes, and assume that phi is defined in the following manner. it takes n tuples its argument and returns product of this n sets, a1, product a2, product so on, so on, so on, an. Then it's possible to prove that phi is injective but not surjective. And counterexample for surjectivity is here. Take x1 ABC, x2 1 2. And now consider the following collection. It contains two ordered pairs, a1, b2. It's contained in the product of x1 and x2. Okay, undoubtedly. But there is no any a1, a2 in power set of this product, x1 product x2, such that product f of a1 and a2 would be equal to this g. You can easily check it, you can calculate it, and think about this for several minutes. There are also other interesting questions like continuity or separation actions or basis, sub-basis. They've been already studied by our authors, and we shall also deal with them in our next videos, probably. Note that it would be interesting to consider product topology of n-ary topological spaces. As far as we know, this issue has not been studied yet. Moreover, one can think that it would be interesting to discuss not n-ary topological space, but, well, infinitely ary topological spaces. But this is beyond the scope of our presentation. Here is the bibliography. The first paper was Topology Between Two Sets by Jyoti and Tangavellu. Then we had many papers on binary topological spaces, and also some papers like here on n-ary topologies, combinatorial properties and the n-ary topology on product of power sets. Thank you very much for your attention.